Hello. Okay, so welcome back to your module 4, moment distribution method. Okay, so we will now proceed on your unit 3, the analysis of indeterminate frames with Sidesway. Okay, so in this unit, these are your desired learning outcomes. First is to understand how Sidesway effect on the structure is calculated. Okay, and then of course to analyze totally your indeterminate frame with Sidesway using your MDM or moment distribution method. Okay, so let's have an example, okay, to discuss that. So determine the reactions of the frame shown below using moment distribution method. Okay, so this is your structure, or actually this is the frame with Sidesway. This is actually what we solved we solved this one from the slope deflection method and the consistent deformation method. Okay, so we should end up with the same answer using your moment distribution method. However, if you will try to recall in the previous unit, I've mentioned about Sidesway, okay, which is not actually considered in moment distribution. Okay, in your moment distribution, we should not first consider your Sidesway, since actually we will separate the effect of that on the structure. Okay, so as you can see, again, this is what happened if I will try to apply the loading on this structure. So that will deflect that way, so you will have that delta, because again your joint B and C is not restricted, okay, or not supported laterally or horizontally. And as you can see, this is a fix and that is a pin, so this could be our elastic curve. Okay, so what will I be doing is, since relative deflection or translation, or that is again what we know as the Sidesway, of a member is not considered in the concept of moment distribution, therefore, the first step is to restrict the structure by considering a support that will resist the joint from translating. So, for us to apply your moment distribution, okay, your moment distribution concept, we should first try to resist the Sidesway. Okay, so how will I do that is to apply what we call this one, an artificial support. Okay, we will try to apply an artificial, or actually that is just a, yes, we call it artificial because actually that is not there, or dummy support. Okay, you can call that as a dummy support for us to restrict the Sidesway, so that what we are just analyzing here is the effect of the external loading without that Sidesway. Okay, and then later on we will try to separate the effect of the Sidesway, and then we will add, okay, that effect on the total structure. So let's say, since again what we are trying to resist here is just the Sidesway, so I will apply here a ruler, say as an arbitrary or dummy support ruler, not a hinge of course, because if that will be a hinge, then that will help on resisting the vertical loading. So you should not do that, since what we are trying to cancel out is just the Sidesway, okay, horizontal translation or deflection. So if I will do that, I will be having this ruler, then I will have that reaction. Okay. So what will happen here is that we will try to analyze this, since this is now a structure without Sidesway because of that dummy support. Then you can now apply your moment distribution. However, that is not just, okay, the effect, or that is not just the analysis of the total. Since what we are going to do later is now to remove that one, let it sway, and then get the effect of your Sidesway, and then add that one to the total, so that if we will try to total, that is the total effect of the whole loading together with the Sidesway on the structure. So let's say M there is the end moments of any member. Okay, so let's say that is your M there, M sub end. Okay, that will identify that is the end moment. Then that is equal to M sub O, for in M sub O is just the end moments, okay, to be calculated considering or restricting your Sidesway. So this is this table. We try to restrict the Sidesway, get the end moments by applying, of course, your moment distribution. Then you will end up there with end moments, and this will be again without Sidesway. End moments without Sidesway. And then later on, we will discuss on how to get that M sub R, that is the end moment due to this Sidesway. Okay, so later on we will now add this without Sidesway, and then later on add the effect of your Sidesway, and that will be the end moments that we will now consider to solve for the reactions, support reactions, and of course, once you have your reaction, you can draw your shear and moment diagrams. So if that is supported in that way, then what happens again? Establish your moment distribution table. So joint A, that is fixed. Okay, joint B, continuous. So you have their connected BA and BC. Joint C is continuous. You have their connected CB and CD. Of course, we will not first consider about that reaction. We will only solve that reaction R once we already have your end moments. Okay, and then joint D, that is a pin. Okay, so if that is a pin, then no need for us. And actually, that is just a single member connected at D and A, so we do not need actually that distribution factor. And remember, your fixed support, we do not need to balance that since the support will receive the excess moment. In your pin, we need to balance that totally. Okay. However, in your fixed end moments, there is no member load at AB, so 0 fixed end moment at AB and so with BA. At your BC, okay, that is again WL squared over 12, but in your left side, that is trying to counteract this deflection because of that 2 kPa. So that will turn counterclockwise, so it's a negative 150. And then CB is a positive 150. WL squared over 12 is T. And your CD, there is no member load, so that is 0. CD and DC. Okay, we do not have joint load. So again, if you have there, let's say, a moment at joint B, all you need to do is consider that for the total joint B. Okay, you do not need actually to distribute. All you need to do is write that as a whole, since actually we will submit all of that. That is the moment at joint B. However, we do not have, so that will be blank in all of the joints. Okay, now there is nothing to be balanced, but in here we need to balance that fixed end moment of BC, which is negative 150. So you will balance that by a positive and then multiply or divide it with respect to the distribution factor. So 2/3 of positive 150, since we are balancing, is 100, and then 1/3 of that is 50. And then in here, same thing, but your only distribution factor will be different. By the way, okay, this is fixed, so I over 15, I over L. That is I over L, since considered fixed, it is continuous. And so with CB, okay, I over 30. And then this one is actually 3/4 of the I over L. Why? Because that is simply supported on the other end. And of course, we do not need this, since that is just a simple support. Okay, so now, again, that is how we ended up with your distribution factor. This divided by the summation, this divided by summation. Okay, so where are we now? Here. So we balance that one, so 150 to be balanced by a negative. Okay, and then negative 150 multiplied by 2/5 is negative 60, multiplied by 3/5 is negative 90. Okay, now carry over. Okay, carry over BA, since that is fixed, so we'll get 1/2. This is fixed, so get 1/2. Carry over 50, it will be getting 1/2, since that is continuous, so that is considered fixed. And this one will be carrying over 1/2 of that, since the same, continuous, so fixed. But this one, okay, I will be carrying it over, but there should be no moment to be transferred, since that is a simple support. So, okay, that is still 0. Now balance. Okay, nothing to be balanced, so still 0. Balance this, the same thing. Okay, so this is positive, so you will end up negative balancing. Multiply to 2/5 is negative 10, that will be negative 15. Balance this is the same thing, that will become positive. Multiply to your factors, you will have this. And then now another, since again your balance here is not yet 0 or not yet close to 0, so we need to continue. Another cycle, carry over half of that, carry over half of that, carry over half of that, and nothing to be carried over, since that is just a simple support. Balance again, and then balance, the same process. Okay, so this will just become a negative balance, multiply there, and there you will have 2 and 3. And then same thing here, you will have 10 over 3, 5 over 3. And then, by the way, in here, we do not need to balance, since that is a fix again. So there is no need for us to balance on your AB. And then if you will try to carry over it again, since that is not 0, this is still more than 1, and so that. So carry over, carry over, carry over, carry over, so 0, balance, 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 no need to balance. 2/3 is 0.67, and that is 0.33. It is a little big. It is a little bit big, and that is 0.33, and that is 0.5. So we need to maybe apply one more cycle. So carry over 0, since that is a pin again. Carry over half of that, 1/6 carry over, and then carry over, and then balance. You do not need balance. Will give us now. I will show you the decimal so that we can see if that is almost close to 0. Yes, that is already 0.1, so maybe we can stop. 0.06, yes. 0.07, 0.1. So that is now negligibly small. But if you still want that, or what you want is 0.01, you can still repeat the process again and again. But the effect on that will still be small. Okay. So now all we need to do is summate. So these are your end moments due to the external loading considering without Sidesway. So this is your end sum O. So now let's proceed with the effect of your Sidesway. Okay, so now for us to let that Sidesway happen, we will now try to remove the artificial support and let it sway. Okay, let it sway. And then the relative deflection or translation, or we call that one as Sidesway, is now due to the lateral force equivalent but opposite direction to the reaction of your artificial support. So how do we analyze this Sidesway is we will try to compute the equivalent force of that and apply it on the structure, so that instead of the Sidesway a while ago on the total original structure, the Sidesway is now separated, and that is the same to the effect of the force that we will try to apply. We call that one equivalent force, equivalent to the effect of the Sidesway. So what is that? Actually, the Sidesway is resisted because of that R, isn't it? So the only thing that stops the Sidesway is your force R, or your reaction R. Therefore, to let that the Sidesway happen, all I need to do is release that one and then apply your R on the opposite direction, so that that will sway on the same direction as we had before. But of course, this time you do not need now to be, we need to remove now your external loading, since we already analyzed that one. Only the opposite direction of your reaction, so that we will let it sway. Okay. Again, you do not need to be considering the external load, since we are done with that. However, for us to know that R, we need to make use of this. Okay. So get this equilibrium at joint C, then you will end up with reaction R. Or simply, if you will try to cut your reaction, your support, in support you will try to actually uncover your shear here and shear, so that these are horizontal forces at A and D. Semi horizontal, you can still end up with R. Okay, together with your 10 kips. But what I did here is that I transferred my end moments to our members. So that is positive, so these are clockwise. I will solve the end shear. Okay, so they are both positive, so that is clockwise. And if I will summate at joint B, that should be countered by counterclockwise. So this is my shear. So sum that one divided by 15, you will have 12.41. Opposite direction will be the shear on the other side. Okay, that will be transferred, since that is a horizontal force. Transfer there will become going to the right. Together with your 10 kips, if you will add that here, that will be 22.41. That is the axial on your BC. It will go to the right, it will go to the left, and it will go to the right. So that is the effect of actually your shear and your 10 kips on your joint C. Why is it we are transferring it at joint C? Since we need that R. And then what else that will affect that one is your shear in your CD. So same thing, MCD is positive 108, so negative. So that is counterclockwise. So to counteract that one, going to the left, VCD, this divided by 15 is 7.24. So that will go now to the right, that will be transferred to the left. So as you can see, the FCB, the axial at CB, is reduced by the shear on your CD. So this axial here is 22.41 minus the 7.24. You will end up with a reaction. Okay, this is your artificial or your dummy reaction R to be 15.17 kips. Okay, that is the reaction. But for us to let that sway, remove that one and apply it the opposite direction. So that will now actually what do you call this one? Okay, sorry, that should be prime only. Not That should not be with prime. Okay, so again, I just remove that prime. That should be delta only. Okay, so again, if I will have to apply our R, or let's say that is now our force R in the opposite direction, so let it say, and that will now be your delta. So again, the effect of the external loading a while ago, which is delta, is now actually uh, the effect of your reaction a while ago, but opposite direction. Okay, so that will be delta. Okay, so now we will try to analyze this effect of your R and of course your delta, or that is actually the total effect of the sidesway to your frames, okay, or to your member of the frames. So how is that? So if you try, okay, however, okay, you'll try to read this one. However, the effect of artificial force R cannot be determined by moment distribution as discussed previously since translation is involved. So again, as I've said, you cannot apply moment distribution, okay, if there is a translation, okay, that is involved. Since actually that is not considered for our formulas. However, okay, if we can consider there, instead of applying that delta and your R on the structure, instead of applying your R and then finding that value of delta, all we need to do now is try to reverse the process. I will now be assuming a deflection. So let's call that one as delta prime, okay? And we will be considering that one, and you will solve the equivalent Q. Okay, so let's forget first about R. Since again, you cannot end up with you cannot use this one with moment distribution and then be solving that delta. Okay, delta effect. So what we will be doing is we will now try to reverse the process, assume a value of whatever delta that we will be assuming, and then solve for whatever equivalent force, which is the same line of action with your R. Okay, and then we will solve that Q, and then later on we will determine the effect of that delta. We will now go back to the effect of this delta here, original delta, by applying your ratio and proportion or proportionality with the forces R and Q, isn't it? If you try to recall the unit load method, applying a unit load will actually have the same what we call this one effect, only that this is smaller compared to a bigger force, isn't it? So that is how we analyze your unit load. So if you still do not know the force, apply a unit load, and then if you already know the force, the effect of all of that will be of that unit load. All you need to do is multiply by the total force. Okay, so that is the same concept that we are trying to do here, but of course that is not one, since again it depends on what value of delta you will be assuming. If I will assume a delta and I will be ending up with a Q, then the effect of that should be proportional to the effect of R, okay, as the original delta. So by ratio and proportion, okay, you can say that the ratio of your original force R with your equivalent or assumed force Q should be the same as the ratio of their end moments. So whatever member you are considering, the ratio of that R with Q should be the same as the ratio of the end moment caused by the R and then all over the moment caused by the force Q. So by ratio and proportion, we can actually if you need, since okay, what we need here is M sub R, okay, the effect of your sidesway. What we need is the effect of R. But again, you cannot get the end moment directly because there is a sidesway. So what we will be doing is by ratio and proportion. Okay, so now cross multiply, you will have your M sub R, that is now the end moment of any member due to the sidesway, and that this will be cross multiplied there. So R over Q times whatever end moment caused by that delta that we assumed, and the Q will be now proportional to your effect of the force R by using, of course, proportionality. So let's proceed now in solving that end moments due to your Q, and then of course we will first solve that Q by assuming a value of your delta prime. Just assume, okay? So that is our next step. But okay, for simpler solution, instead of assuming, okay, you can assume your delta. However, it will be a little bit hard for us to assume It's okay. It is simple, but it will be having a little bit more solution than if we will do this. Okay, because if you will try to assume a delta, you need to consider that that is a very small number, isn't it? Let's say if you are on keep fit, then your deflection only should be in inches and so on and so forth. If that is in meter, kilonewton, that deflection should be only millimeters. So instead of doing that, okay, since actually that delta will end up with an end moment, okay, that delta that we will be assuming will end up with an end moment. If you will try to deflect that one, this will end up with a moment on the ends of the members. So instead of assuming a delta, I will now be assuming the entire, okay, fixed end moment or end moments, okay, end moments of our, let's say that it should be entire FEM, fixed end moment, or I can say that it's just end moments. Okay, so again, instead of assuming for the delta prime, I will assume for the total value, for the whole value of the end moment. Okay, so please pay attention about this. How do we get that end moment? Isn't it that we do not have these member loads? Of course, we only have that. This is a joint load, will be considered as a joint load, but in the first place, we do not know that one. That is what we are trying to get to ratio to your force R. So, you cannot make use of your fixed end moment formulas. So the end moment is actually from your slope deflection equations. Okay, since again the moments are due to the deformation, not due to a force, we will be using your delta and theta to solve that moment at the end. Okay, so that is again from your slope deflection equation 2ei over L. That is, okay, if you are considering joint A, that is 2 theta A plus theta B minus 3 delta. What is delta again? That is your relative, if you say relative deflection of a point with respect to the other end. And of course, plus if EM or the fixed end moment due to the external loading. However, again, since we removed all the external loading, since we are only focusing on the Sidesway, there should be no fixed end moment. So that will always be 0. Okay, so we will only focus on your theta A and theta B. Okay, so if you'll try to consider member AB, this is considered to be fixed. This is still fixed since that is of course continuous. So your theta A and theta B are 0. You will only have there a delta prime, the one that we assumed. Okay, and this is you need to consider this also. Okay, this is important. It's okay you will consider any sign, but you will end up with a negative values of Q and so on and so forth. So you might be confused about the value of a negative. But if ever let's say you assume this one incorrectly, you assume the other way. For example, you still do not know how to target the elastic curve. Then maybe you will end up with the opposite. It means only that you will end up with a negative Q, but still that will reflect on the ratio of your Q in there. You need to reflect the sign. If you will end up with a negative Q. But for us to to stick to a positive value, you need to consider, if you want, you can consider the sign convention. Since that is deflected to the right, again, we are assuming to the right is positive. So if delta is positive, delta prime, so that will remain negative. So again, everything will be 0 except for that. So if you will simplify together with that is 0. Simplify will be a negative 6ei delta prime over L squared. Same thing, even if you try to solve your BA, what happens is that theta A and theta B will interchange. However, your thetas are 0. So still, this is a negative 3 delta prime over L. Delta is still positive even if that is considered on the other side, because still, we assume that that is going to the right. So, that both AB and BA are moments which are negative 6ei delta prime over, okay, L and L will be L squared. Okay. Why is it negative? Actually, you can actually check that one, because look at this. If this will bend that way, for that to be still slope 0, the moment should counteract counterclockwise, or should resist that counterclockwise, so that of course that will not bend just like a free support. That's why you ended up here actually with a negative. And so with that, okay, there is no force in between or in the member, so there will be nothing that will counteract that one, only the shear. Okay, so of course if you will try here, that will also be, as you can see on the bending, that should resist. Okay, it counterclockwise, so still it counterclockwise. So that's it for a fixed fix. Okay, but you need to consider the sign convention for delta for if you want to end up with a positive value of Q. Okay, you will need to consider that going to the right is positive. So AB and BA is negative 6EI delta prime over L squared. Now for member BC, even if that is fixed, however, okay, fixed because this is continuous, but theta, since these are fixed 0, 0, and at the same time your delta is 0 since there is no delta for member BC. That delta is only for BA. This delta here is only for CD. Since again, delta is deflection with respect to the other points. So if you try to look at this, originally B and C are the same elevation. And even after the deflection, they are still the same elevation. Okay? So there is no delta for BC. Therefore, 0, everything is 0. So your BC is 0. Okay? BC and CB is 0. However, again, if there is a delta involved, you will end up there with negative 6EI, whatever that delta all over L squared. Now to your member CD, this is now a fixed pin or a fixed simple support. Okay, it could be a fixed pin or it could be a fixed ruler. The effect is the same. So in your CD, since by the way, the only additional or the change with your AB is that since in fixed both thetas are 0, in your fixed pin, there is now that rotation at 20. So you will end up there, again, delta is positive going to the right, so that will remain negative. So you will end up with this equation. However, if you try to get your MBA, even if you have this value or equation here, that MBA should be 0. I'm sorry, that should be DC. Okay, let's just change. When I am doing this, I am actually copying the formula DC. Let's be DC. And then pasting that one. So it ended up AB. Okay, so DC, even if you have this equation, but that should be 0 since that is a simple support. So there should be no moment at 20. Okay. However, for us to simplify this, because of course, what we are trying to have here or to assume is delta prime only. So there should be no rotation. So from your equation DC, MDC, I can actually play around with this. Look at this. If that is 0, this is to be cross multiplied there. That will be useless, 0. And that is 0. So you will end up with 2 theta d minus 3 delta prime over L. This will transfer now on the other side as positive. 3 delta prime over L, and then 2 will cross multiply down so that you will get the value of theta d. Substitute back here on your MCD. Okay, so that we will simplify that only in terms of delta prime. So substitute that. So 3 halves, or that is actually 1.5 minus 3. Okay, delta prime over L. So that is the variable, but this will be 3 halves minus 3, or 1.5 minus 3 is negative 1.5 or negative 3 halves. Multiply it to this outside is 3 halves times 2 will cancel out 2, you will end up with 3. And then L squared, and then EI, and of course your delta prime. Delta prime. So negative, because of the positive, or we assume that to be going to the right, so positive. Okay, however, you need to consider again your DC is 0, even if we have that equation, but that is 0. So you can write that as simple as 0, so that you will not end up with longer solution. Now, we have all of this. We have these equations in terms of theta prime. So now, if we assume theta prime, you can now get your end moments. Once you have your end moments, use your distribution, moment distribution to distribute or to balance all the joints, and then that is now the effect of your Sidesway. However, again, as I've said, instead of assuming that theta prime, or delta prime you can now actually assume for, okay, let's say I will start with BA. I will assume for an end moment of BA or AB, then solve for the rest. Okay, that is how we will do it. But if you want, you can still assume for delta. But okay, you need to consider that maybe the delta is just very, very small, so that if it is in feet, that should be inches only. If that is in meter, kilonewton, that is millimeter only. But again, I suggest this one. Rather, instead of assuming a delta prime, assume for the entire end moment. But you will only do that for one end moment, and then the rest will be solved based on that assumption. Okay, so for me, I will let MAB and BA, since that is a negative. Okay, we predicted that as a negative, so let me assume a negative. But if you assume a positive, it is still okay. It will still reflect, okay, on the side of your cube. Okay, so we're good. So again, that is a negative, so I will assume a negative 100. It's up to you. You can assume negative 10 or negative 1000 if you want a bigger moment. So if that is a negative 100, and then that is your MAB, MBA, so that is what I will input on my moment distribution table for MAB and MBA. Okay, so now I will be solving the EI delta, since again EI delta in this problem is constant, isn't it? So that will not affect. Yes, since EI is constant. Yes. But again, if EI is constant, I mean it's not constant or variable, all you need to do is change that one with the value of your EI. Okay, so EI delta prime, so cross multiply this, 15 squared, cross multiply, negative negative cancels, divided by 6, you will end up with a positive 3750. That is the value of the entire EI delta prime. And then for this EI delta prime, I will be using that to solve for the rest and moments for the other members. But even if I will do that in your BC, that will still be 0. Since again, I've explained that one a while ago. There is no delta for that. So MBC CB is 0. So there is no end moment initially for BC and CB. And then of course, substitute that in your CD. Okay, 3750. That is your EI delta prime. You will have 3, that is negative. Your length is 15 squared. So that is a negative 50 cube feet. So that's it. And then DC is still 0 since that is simple support. So as you can see, you have your end moments assumed. However, comparing these ones, consider joint P. Moment MBA is negative 100, but moment BC is 0. So in that joint, this is not, or the joints are not in equilibrium. So now we will try to balance that by distributing the moments, and that is now when we will be using your moment distribution table. Okay, so the same thing. Actually, all you need to do is use the table that you used before, only that you will be changing the moments. Okay, so by the way, so if you use an Excel to do this one, to accomplish your table, all you need to do is change this value that will reflect directly since you already programmed your cells. Okay, but if you do it manually, then you need to recompute it, balance, and then of course your carryover. Okay, so again, MABBA is negative 100, negative 100, negative 100, 0 for BC, since again there is no deflection for that, so there is no initial moment for that. And then CD is negative 50, and then DC is 0. Okay, and there are no joint loads since we are actually just considering here your what we call this one. We are just considering the effect of Sidesway. Okay, you can change that one to end moment since actually that is not technically a fixed end moment. Or you can say that it's a fixed end moment, but actually that is just an end moment due to the deformation delta prime. Okay, so it's up to you. So now these are my loads. I need to balance that. Okay, I mean I do not need to balance that since that is a fixed, so that will be carried by joint A or by support at A. This one I need to balance it. Okay, so the same thing. This is a negative, so that will be a positive balancing multiplied to your distribution factor. In here a negative, so positive distribution factor. You do not have load, so nothing to balance, 0. Carry over, this will be carried over, carried over, carried over, but 0 since that's P. So repeat the process, okay, again and again up to the time you will end up here again with your balancing, which is almost close to 0. That is just almost 0.1. Same thing here. So maybe we can stop, but if you want, you can continue. Okay, but that will just be a small effect on your summations. So summate, you will end up with a negative 69, summate, negative 3793, positive 3793. So same thing, you need to check the equilibrium at the joint. And this one, equilibrium at the joint. So we're good. And that should be 0 since that is a pin. So we are good. But what is this moment? That is the moment due to a force Q. or due to your deflection delta prime. So that is not what we will be using, since what we need is the m sub r, isn't it? Add that m sub r to your m sub o, you will end up with the actual end moment. But what we have is m sub q. And again, what I've said is all we need to do is use what we derived for the ratio and proportion a while ago for the value of m sub r. Since once you know the value of q, you can apply that, since again they are on the same line of action, so they have the same what we call this one, flow of effect on the figure or on the structure. So what happens is that all you need to do is apply ratio and proportion on the values of your forces, and of course on their effects, which are your end moments. So again, that's it. We had this one that is m sub q due to the force q. But for us to apply or to use the ratio and proportion formula that we derived, we need to get that q. So the same thing, just like how I ended up with r. Okay. So get the shear here, transfer there. Of course, there is no 10 kips here already, since that is only for the external loading. So that VBA will be your BC, or the axial at BC. We do not need to be getting the shear at BC, since we do not need that yet. Okay, so transfer, transfer, transfer. And then the shear here, transfer. Okay, so they are the same direction on the left side. So your Q is correct. We assume that to be on the right. So that is 9.08. So as I've said a while ago, if you assume a negative or a different sign here on your, if you assume a different sign on your formula for the end moment, you will end up actually with an opposite sign, or it means the other way. But you need to carry that one in your ratio. Okay. So that is 9.08 summation of your VCB, which is equal actually to your this one, 7.13, plus that 1.95 is now 9.08. Okay, that is now our Q using our ratio R over Q times whatever the end moments. Okay, I just simplified it here. I copied. So this is your M sub O that is coming from your a while ago, this one, due to the external loading without Sidesway. So I copy this. Okay, this is your M sub O. Okay, so that is our M sub O. And then this is M sub Q, but that is not what I will be adding. I will be using that to get your M sub R. So again, using your ratio, your R is 15.17, your Q is that 9.08. So whatever the moment at a joint, we will get the moment due to R by multiplying this ratio. So multiply 15.17 over 9.08 to your negative 69 will give us, okay, that is your M sub Q, will give us an F sub R of negative 115.28. So same thing happens. This ratio multiplied to that will give this, multiply to that will give that, multiply will give, and then so on and so forth. So now you have your M sub O and then M sub R. Then again, what is that? The actual end moment due to the external loading together with the Sidesway is now just adding your M sub O and M sub R. So M sub O, this green here, and the M sub R, that green there. If I will summate that, will end up negative 53 for joint. This is joint A, by the way. This is joint A. I forgot to put that, but that is joint A. Negative 53.28, and then that is joint B, and that is joint B, that is joint C, and then this is joint D. So again, you need to check that. Going to your actual scenario, joint D, that should be 0 since that is a pin. This should be equilibrium, so we're good. Summation is 0, summation is 0. And it's okay, you have that moment since that is fixed. So actually we solved this one before, isn't it? So now the same thing, apply your end moments on the member, end moments, and then get your end shears, end moments, get your end shears. Same thing as our solution on slope deflection and your consistent deformation, okay? Only that, of course, we did not end up with an exact value because, of course, these are rounded values. But if you will compare the result on our final reaction using these three different methods are actually close with each other. So before, in your consistent deformation and in your slope deflection, we use the whole number or the whole fraction. So this is actually 53.16, but this is now 53.28 because of the rounding. And this is supposedly 0.51, but that is now 0.50. But it's okay, that is just small. And this is 10.51, but that is now 10.50. And this is the same actually. So that is analysis of indeterminate frame with Sidesway using your moment distribution. So this is what you should put in mind, okay? The effect of translation or the Sidesway to the structure in using your moment distribution is to be analyzed separately from the external loadings. So how to do that is to restrict your Sidesway and then get the equivalent force of that to be loaded as a separate load on the effect of your Sidesway. And of course, in analyzing the translation effect of Sidesway, an arbitrary value, since again you cannot use if the force R and then solve for the deflection delta. And distribute. First, because of course, if you try to look at this, if you have that R, there is no way you will solve the end moments, isn't it? You cannot solve the end moments due to that R. Even if you try to think of a way to solve that one. And again, that R will give an effect due to that delta. So again, there is no way for us to solve for the moments at the end joints of your members using that R, since that is actually not a member force. So you cannot apply that as, you cannot solve the fixed end moment of any member of this. So you cannot use the moment distribution. Therefore, what we are going to do is, instead of the force, what we will be having is the deflection, since there is a way for us to compute the end moments using a deflections. So that is how we ended up here. Use now your end moment equation, dealing with delta and theta, your rotations and deflections. Okay? So that is how we ended up with your table here for us to have your end moments. Okay? So again, so that is the important concept. You cannot solve the effect of your force R because there is your Sidesway, and actually there is no way for us to be solving the end moment. So what we will be doing is assume an arbitrary value of that translation. So we will be assuming a value of translation, and then whatever that effect of that, we will apply ratio and proportion for the values of R and Q, and of course to their effect on the end moments. So that is your flow of analysis of indeterminate frame with Sidesway using moment distribution. So first, if there's a Sidesway, restrict the Sidesway. Solve for that restricting reaction or the dummy reaction, and then apply it as a force to again to bring back the deflection, and then analyze it separately, just like what we did by ratio and proportion. Okay, so on and so forth. So you will expect here two moment distribution table for the external loading without Sidesway, for the assumed value of deflection. Okay, and that table for the assumed value of deflection, you will get the value of the effect of deflection of the actual deflection by ratio and proportion, and then add this table with the derived value due to deflection. So add this one, and this will be your end moments on the actual end moments due to everything, due to the external loading together with the Sidesway. Summate, and then of course just like what we did, if you have your end moments, get your end shear, transfer on the joints, solve for reaction. Once you have reaction, you can solve your shear and moment diagram, or you can draw your shear and moment diagram. Okay, so that's it. This could be our, yes. Okay, so if you have any question, you can comment below, or again, that's it. You can comment below, or we can discuss this one on the live meeting. So thank you very much for watching.